All right, ladies and gentlemen, it's been quite a while since we've needed to use our calculators. As a matter of fact, I would claim that the last two tests you could have gotten away with not even getting your calculator out of your book sack. But for the remainder of the semester, unfortunately for those of you who are mathematically challenged, we are going to be using the calculators and doing computational numeric aspects of chemistry. And we're going to begin with a series of unit conversion problems, much like we did on our first test. Now, these unit conversion problems, unlike the ones that we did before that were related to essentially metric units and interconversion between English and metric units, just to whet our appetite, so to speak. Now we're going to do unit conversions that are specifically related to chemistry. Because, of course, one of the things we want to be able to do is deal with materials that individually are quite tiny. So we have these atoms and molecules and even electrons and subatomic particles that we might want to work with. However, they are essentially imperceptible, and we can only really infer their presence at small numbers by using tricks like shining light on them. Well, what we're going to do to weigh out or deal with samples of matter, since we can't deal with them on an individual basis, we'll deal with large numbers of them at the same time. And in doing so, we will introduce one of the more fundamental quantities of chemistry, and that is the quantity known as the mole, which is really a shortened form of the word molecule. And a mole, which is often abbreviated MOL, I don't know why, but it's very common that you will see MOL. It is the so-called SI unit, or System International Unit, of counting the amount of matter you have present in a sample. 1 mole of matter is the amount that is contained in exactly 12 grams of carbon-12. Now, when I say exactly, I mean exactly. That should be 12.00000 to all units of significance. Then we would know exactly how many things are in a mole if we have exactly 12 grams of carbon-12. Now remember, carbon-12 is an isotope of carbon. It's a particular form of the carbon nucleus which has 6 protons and 6 electrons in that nucleus. Now, of course, a neutral carbon-12, which these are all supposedly going to be, would also have 6 electrons buzzing around that nucleus. Now, this number of things, which is present in 12 grams of carbon-12, is known as Avogadro's number. Avogadro's number is the number of atoms in exactly 12 grams of carbon-12. Now, initially there was a lot of debate about what should be used as the standard. Physicists argued that oxygen-16, O16 with 8 protons and 8 neutrons in an oxygen nucleus, should have been used as the standard. Then if you weigh out 16 grams of oxygen-16, you would have exactly a mole. Now it turns out that that's close to the same as the number of things in 12 grams of carbon-12, but it's not exactly the same to all digits of significance. So in any event, the chemists won out, and Avogadro's number is defined relative to 12 grams of carbon-12. Now I want to point out to you that Avogadro had nothing to do with the establishment of this number. It is simply named in his honor. He was a very important Renaissance man and chemist in the first half of the 19th century. And again, Avogadro's number is named in his honor. He really had nothing to do with establishing what it was. So 1 mole of things is 6.0221367 times 10 to the 23 things. And you see below that, I write that out in numeric form from the scientific notation. It's a heck of a lot of things that are in a mole. 602 septillion things in a mole. So if you have a mole of carbon-12, it has that many things. If you have a mole of O16, it has that many things. If you have a mole of H2O molecules, it has 6.02 times 10 to the 23rd things. If you have a mole of electrons, you would have 6.02 times 10 to the 23rd electrons. Now, of course, realize this is a real number and should have much more significance or digits of accuracy than the 8 digits I'm showing there for the number. But we will typically use Avogadro's number with 3 digits of accuracy. We will use it as 6.02 times 10 to the 23rd almost invariably. And I will also mention to you that this is a very important number in chemistry, and it is one that you should really know off the top of your head. The mole is essentially the bushel basket of chemistry. Because atoms and molecules are so tiny, the mole has to be such a huge number. Literally, a mole of carbon-12, of course, which again we defined previously to mean 12 grams of carbon-12, will easily fit in the palm of your hand. So what we're doing with the concept of the mole is we're defining a usable, tractable, definable amount of material that we can work with in the laboratory. Now, for some materials, it turns out that even a mole of it is tiny, and for other things, it turns out that a mole of it is quite a large amount of it, or at least takes up a lot of space, we'll say. Now, all things that are in a mole have exactly the same number of things in them, but it's, again, going to be a matter of just how much space those things take up, which will define how you're going to have to store them and such things of that. But chemists have decided upon 12 grams of carbon-12, counting out exactly what is in that 12 grams, and you would find 6.02 times 10 to the 23rd atoms of carbon-12. So that is what we are going to use to define this measuring unit. And what you should, again, think of it like, is what, as I'm showing in this picture that you see, it's much like we use for a case of beer, that's 24 cans of beer, like for a gross of pencil, that's 12 dozen or 144 pencils, for a ream of paper, like 500 sheets, and like a dozen eggs is 12 eggs. These are just counting units that are commonly employed in commerce when doing business and using these things, because buying pencils by the individual pencil is just something that makes it such that it's not a tractable amount that we would commonly do that kind of purchase with. To get some perspective on just how big a mole is, why don't we ask the question that if we were able to stack a mole of pennies and we just place them one on top of the other, how high would that stack of pennies reach? Well, I measured a penny, and it turns out a penny is about the 2 digits 1.4 millimeters wide. So if I convert my millimeters to meters using the conversion you see there, then multiply that by 6.02 times 10 to the 23rd, or a mole of pennies, I would find that a stack of a mole of pennies, with each of them being 1.4 millimeters on its edge, would be to a height of 8.4 times 10 to the 20 meters high. Well, let's do some comparison to other objects to see just how high up that mole stack of pennies would be. Our stack of pennies, that is a mole high, or a mole stack, has 8.4 times 10 to the 20 meters high. Well, the Empire State Building is 3.8 times 10 to the 2 meters high. So we got to go a little bit further. To the top of Mount Everest is 8.8 times 10 to the 3 meters, 8,800 meters. Got to keep going. To the moon is 3.8 times 10 to the 8 meters. I think I said at the beginning 8.4 times 10 to the 8 meters high. I meant 8.4 times 10 to the 20 meters high is how we got to go for our mole stack. So to the moon, we're not still quite there yet. The distance to the sun is 90 some million miles, and in meters that is 1.4 times 10 to the 11th meter. So our stack of a mole stack of pennies goes past the sun. The next nearest star is 10 to the 16th meters away. Nope, we're not quite there yet. The distance across the Milky Way, our galaxy that our planet and solar system are in, is 9.5 times 10 to the 20 meters across. So our mole stack of pennies would extend the distance across the galaxy. Now, we really can't fathom that as from a perspective of just how big that is in actuality, but I think we get the idea. A mole is a lot of stuff. And the reason a mole has to be a lot of stuff is because individual atoms are so small that we have to have a huge number of them present before they begin to become perceptible. Now think about the concept of the mole in terms of, say, an empirical formula for some compound or molecule. Previously, we used the designation for this particular compound C2H6O, which turns out to be ethyl alcohol. If we had one molecule of C2H6O, we perceived it as having 2 atoms of C, 6 atoms of H, and 1 atom of O. Well, the point I'm getting at is we would not have atom tweezers or even mole tweezers for that matter, but we just can't simply deal with individual molecules and the individual atoms that make them up based on the technology we have available to us in the laboratory. Even the most advanced laboratories on this planet could probably not deal with a single molecule and the atoms that are that constitute it. So what we will now, from now on, think of in terms of when we look at this is not one molecule of C2H6O, but one mole of C2H6O, or an Avogadro's number of C2H6O atoms. Then in 1 mole of C2H6O, there are 2 moles of C, because there's a 2-to-1 ratio to the C per molecule. So that would mean in 1 mole of C2H6O, there would be 1.2 times 10 to the 24 carbon atoms. Now, where did I come up with that? Well, that is 2 times Avogadro's number. 2 times 6.02 times 10 to the 23rd would be 1.2 times 10 to the 24th atoms of carbon in that 1 mole sample of ethanol. In addition, there would be 6 moles of H in that 1 mole sample of ethanol, and there would be 1 mole of O's. And again, in our 1 mole sample of ethanol, there's 6.02 times 10 to the 23rd oxygen atoms in that collection. Even though we have now defined this quantity that we call the mole, that does not make it the go-to trick for chemists as we are determining how many atoms or molecules of a particular type we are using in a sample. And the reason is that if you were asked to add a mole of a certain material into some chemical process and you were scooping them up by individual atoms at a time, that would be a little bit problematic because you would be counting not only for the rest of your life, but probably for the rest of your subsequent generations of many of your progeny's lives as well. So what we do is a trick that has long been employed in commerce when you have tiny things that you wish to sell. You don't sell them by the individual, you weigh out a quantity of them and you infer from the weight how many are present. So a bag of M&Ms is not sold by the M, it's sold by how much the bag weighs. A box of cereal, same thing. A bag of, even like in the good old days at when you went to the hardware store, you did not get individual nails. They put them in a scale and weighed the nails and then charged you 10 nails for a penny based on the weight of them and things of that sort. So we are going to employ the same trick that has been employed in commerce. What we will do, if we want to use a certain number of, say, oxygen atoms and a certain number of cadmium atoms in a given chemical reaction, we will go to a scale, weigh out a given amount of that material from which we will be able to imply how many atoms of cadmium or oxygen we put on this, we're using in our reaction. And those of you that are in laboratory, I'm sure, are familiar with this. We weigh out reagents all the time to get an inference as to how many are present in the reaction. So what we have then is a conversion factor between the mass of the material and how many of them are present in that sample. And the number present is this standard bushel basket of chemistry, and that would be the mole. So what chemists use is the molar mass of a sample. Now, many people call these atomic weights, but really more correctly, we're going to refer to them as molar masses of the various elements. So someone has determined, and believe me, these have been determined for quite some time now, that if you weigh out 1.0079 grams of hydrogen atoms, then at least to 5 digits of accuracy, you have 1 mole of hydrogen atoms, or 6.02 times 10 to the 23rd hydrogen atoms. If you weigh out 12.011 mole of carbon atoms, you have an Avogadro's number of carbon atoms, 6.02 times 10 to the 23rd of them. A mole of oxygen, as you see, weighs 15.9994. A mole of ions atoms, to get an Avogadro's number of them, you would weigh out 55.847 grams. And then, of course, krypton, you see 83.80 grams to get an Avogadro's number of those. Now, first of all, why must you weigh out different amounts of them in order to get the same number of them? That's because, of course, each of these atoms contains a different amount of nucleons. So the number of nucleons being different in each case, and of course each nucleon has its own individual weight, so that there's a much different weight for the same number of all of these various atomic types. Now another maybe interesting point here is, wait a minute, it says for the second one, if I weigh out a mole of carbon, I have to weigh out 12.011 grams. I thought that Avogadro's number, or the mole itself, was defined relative to carbon. So why do I not have to weigh out exactly 12 grams of carbon when I weigh out a mole of carbon? The reason for this is the relative abundance of naturally occurring isotopes of carbon-12. We'll see out of carbon atoms, excuse me. Carbon-12 constitutes over 98% of all carbon atoms that you scoop out of the ground, but there's a smattering of 1% of carbon-13s, which have an extra neutron and are slightly heavier when you scoop carbon atoms out of the ground. So when you weigh out a mole of carbons, we're not going to separate the carbon-13s from the carbon-12s because they have the same number of electrons. Their chemistry is essentially exactly the same, so we don't worry about them in most typical chemical processes. So we just imply, when we scoop up carbon, all the relative abundance of all isotopes, and we mass average them, as we will see later. We've already seen how the periodic table provides a wealth of information about the electronic structure of atoms. Now we will also add to that wealth of information the fact that the periodic table also lists the number, or I'm sorry, how much of each of the individual elements you would have to weigh out in order to get an Avogadro's number of them. So as you see here, if you want to get 6.02 times 10 to the 23rd silver atoms, you should weigh out 107.9 grams. If you want to get 6.02 times 10 to the 23rd carbons, you weigh out 12.01 grams. To get 6.02 times 10 to the 23rd sulfurs, you weigh out 32.07 grams. I would also like to point out to you that if you look in the periodic table of various types of periodic tables, you will note that they very commonly list different significances for various elements as to how many you need to weigh out for a mole. For instance, elements like hydrogen and fluorine are often listed in these tables to 7 or 8 digits of significance, whereas elements like nickel are listed to only 4 digits of significance. The reason for this is that many elements like nickel come in different isotopic ratios depending on where they are mined in various regions of the world. So in consistency, the accuracy to which the various isotopic ratios for nickel can be mined and determining its molecular weight from that is only accurate to 4 digits of accuracy for something like nickel compared to fluorine, which does not have naturally occurring isotopic forms. So we can weigh out a mole of it highly accurately, no matter where you mine it on Earth, because all atoms that you're mining are exactly the same. Explore this concept of naturally occurring isotopic forms a little further. Here I show some of the naturally occurring isotopes of 3 of our common elements of the periodic table. First, we have carbon, which mostly occurs as either carbon 12 or carbon 13. You'll notice though that seems to give 100% if you add those two up. In the atmosphere, there's also carbon 14, which is radioactive and is therefore used in radiocarbon dating. We have then the 2 major isotopes of naturally occurring chlorine. Notice they are 2 nucleons apart. Okay, I have Cl35 and Cl37. Cl37 has 2 additional neutrons in its nucleus compared to Cl35. And there's about 3/4 of all naturally occurring chlorines are of the 35 variety, and about 1/4 of them are of the 37 variety. Notice I list fluorine there as having no isotopes. 100% of naturally occurring fluorine is F19. Then you see that sulfur comes in a variety of isotopes, even though some of them are not present to very major extent at all. Yet, when you scoop up in nature, you're going to get a wide variety of different isotopic forms of sulfur. On this slide, I list not only the relative abundance of the 2 naturally occurring isotopes of carbon 12, but I list the molar mass of those two isotopes of carbon-12. Now, of course, first of all, let's get it clear. I wouldn't expect you to know either the molar mass of the individual isotopes or the relative abundance of the individual isotopes. But if I gave you the relative abundance of each isotope of a different element, of a certain element, and the molar mass of that particular isotope of these elements, then you should be able to determine the average or relative, or the natural occurring relative abundance of that collection of isotopes that you would scoop out of the ground. What you do is you essentially mass weight the individual masses and sum them together. So essentially, if 98.9% of the isotopes are of mass exactly 12, that means when you scoop up in the ground, 98,900 of them will weigh 12. And then the remaining 1,100 of them, if you scooped up 100,000 of them, would weigh 13.0034 grams per mole, because that 1,100 of them out of that 100,000 that you scooped up would have been carbon-13s. So what I will do, quite simply, to find the average mass of what I'm scooping out of the ground, I will take the relative abundance in a percent form and convert it to decimal by dividing by 100, and then multiply that decimal times the molar mass of that particular isotope. So 98.900% of them are exactly weighing 12 grams. That means dividing that abundance by 100, 0.98900 times 12 will be added to dividing 1.1 by 100, 0.011 times 13.0034. I get the numbers you see below, add those numbers together, and that gives me the molar mass of carbon that I would find in the periodic table. It's the averaged molar mass of all carbon atoms scooped out of the ground. Here I show an example of the same thing, this time using the various isotopes of magnesium. What you will note is that there are 3 naturally occurring isotopes, each with fairly significant abundance. Again, I list the molar mass of each of them as well as that abundance. I certainly would not expect you to know either the abundances or the molar mass, but if I gave you them, you should easily be able to determine the naturally occurring mass that you would find in the periodic table. I divide each abundance by 100, make it into a decimal form, multiply that decimal form into the molar mass of each. Then I just sum those weighted molar masses, and it gives me the total mass that I would find in the periodic table for magnesium, 24.305 gram per mole. More example, this time with nickel, and you can see that nickel has a wide variety of naturally occurring isotopes, some of not very high percentage, but yet they still need to be accounted for when you're scooping them up out of the ground. Again, this is one of the reasons why nickel cannot be reported to a high degree of significance, because of these large number of isotopes and their slightly varying abundances depending on where you happen to mine the nickel. You should practice this one by yourself. I would say cover up the answer, work it out yourself, and make sure that you can come to the conclusion of 58.688 gram per mole for naturally occurring nickel. Fortunately, when atoms combine, there's no loss of mass on the combination of atoms when we form molecules, so that when you want to find the molar mass of a molecule, which we used to call in the good old days the molecular weight, but which I would really prefer you call molar mass, to find the molar mass of a molecule, you simply add the molar mass of the individual atoms that comprise it. Now, what I want to point out to you is the interesting thing about this is that is not the case when you combine the subatomic particles. When you put the nucleus together from individual protons and neutrons, there's a so-called mass defect in the nucleus that results in the binding energy that holds the nucleons together. The nucleus weighs a little less than it should based on the mass of the individual nucleons that comprise it. This is not the case, however, in the molar mass of a compound. For instance, for carbon monoxide, which is C and O, if I find the naturally occurring mass of carbon and naturally occurring mass of oxygen from the periodic table, I can just simply combine them and find that an Avogadro's number, or mole of carbon monoxides, would weigh 28.010 gram per mole. Now again, remember, this is a number that is a real number, so that is knowing the molar mass of carbon monoxide to 5 digits of accuracy. Out to 5 places I know, and in a sense I'm saying I would know Avogadro's number to 5 digits of accuracy as well, since I know these masses to 5 digits of accuracy. So I have 6.0221, actually probably rounded, 6.0222 times 10 to the 23rd molecules of carbon monoxide, and they would weigh 28.010 gram per mole when I do that. On the right, I show the same idea for potassium cyanide, KCN. I turn to my table, find the molar mass of K, find the molar mass of C, find the molar mass of N. Adding them together, I would get the molar mass of potassium cyanide as 65.226 gram per mole. So if a recipe calls for using a mole of potassium cyanide, I would go to the scale and weigh until I had 65.226 grams in order to accomplish that mole. Now, one more thing I want to mention before we leave this slide is the fact that the significance of making the determination of the molar mass depends on how accurately you know each individual atomic molar mass. So if you have atomic molar masses to different numbers of decimal places, then the best you can report the accuracy of their sum to make a molecular molar mass would be only to the one with the limited amount of decimal places. So you have to be a little careful when you're combining these things. If you're worrying about significance in your calculations, it would be best advised to use the individual atomic molar masses all to the same number of decimal places, so that you're guaranteeing you have the molar mass of the molecule to the same number of decimal places accurately. I show more examples of calculating the molar mass of molecules, particularly here those that have subscripts or empirical formulas that have multiple proportions of atoms relative to one another. When you determine the molar mass of these molecules, you have to determine the total mass based on individual atoms present. For instance, I'm showing for carbon dioxide as opposed to carbon monoxide, the mass of one carbon is 12.011 gram per mole, but below that, the mass is 2 times the mass of oxygen. Each oxygen individually is 15.998 gram per mole. 2 of them is 31.998 gram per mole. So the total mass for a mole or an Avogadro's number of carbon dioxides is 44.009 gram per mole compared to the 28 gram per mole that would take to weigh out carbon monoxide. On the right, I show magnesium nitrate. Now notice each mole of magnesium nitrate has 1 mole magnesium, 2 mole nitrogen, 6 mole oxygen. So when I formulate the molar mass of magnesium nitrate, I have to weigh out 1 mole, the mass of 1 mole of magnesium, which I get from the table, find the mass of oxygen in the table, multiply it by 6, find the mass of nitrogen in the table, multiply it by 2, add all those numbers together, and to scoop up an Avogadro's number of magnesium nitrate units, I would have to scoop out 148.313 grams to get a mole of that material. More example, I'd like to do a hydrate. Here I have calcium phosphate pentahydrate, Ca3PO4 taken twice, dot 5H2O. You have to take care in noting exactly how many of each individual atoms is present in 1 mole of this material. There are 3 calciums present, so I'm taking 3 times the molar mass of calcium. There are a total of 13 oxygens. Notice there are 5 from the water molecules, and there are 8 from the 2 phosphates present, so that's 13 oxygens. So I multiply the molar mass of oxygen by 13. Then there are 2 P's in the 2 phosphate groups. There are a total of 10 hydrogens, because in 5 water molecules, each water molecule having 2 hydrogens, that gives 10 hydrogens. And then I just total all those things up, and I get a whopping 400.26 grams if I want to weigh out an Avogadro's number of calcium phosphate pentahydrate molecules. This slide shows some pictures of 1 mole of 5 different substances. Each beaker that you see contains an Avogadro's number of the substance listed. That is, of course, 6.02 times 10 to the 23rd units of each substances. The first beaker on the left contains 6.02 times 10 to the 23rd atoms of sulfur. The second one over contains 6.02 times 10 to the 23rd atoms of iron. Now, interestingly, you will note below those pictures, I show the mass of the contents of each of those beakers. The sulfur beaker would have 32.07 grams of sulfur, because that's how much the molar mass of sulfur is. The iron beaker would have 55.85 grams of iron in that particular beaker, because that's the molar mass of iron. But if you look at the pictures, it looks like there is more sulfur present than there is iron, even though the mass of the sulfur is less than the mass of the iron. Well, that's demonstrating 2 points with regard to the materials. First of all, the iron has a larger atomic number than does sulfur. There are many more nucleons and electrons present in each iron atom than there are in each sulfur atom. So each individual atom is heavier for iron than it is for sulfur. But the reason that the volume of the sulfur looks greater than the volume of the iron is that the density of the iron is greater than the density of the sulfur, meaning the mass to volume ratio is such that the irons are packed in much closer to one another in that element than they are in the non-metal sulfur that you see on the left. So sulfur is less dense, so the same amount of it takes up more volume than the more dense iron, which takes up less volume. The middle picture is a picture of sodium chloride. Of course, I'd have to add up a sodium and a chlorine molar mass to get the total molar mass of 58.44 grams for that sample. Then I have a system known as potassium dichromate. We didn't really use the dichromate anion, but that's what is in that particular beaker. Pretty red color, but pretty nasty stuff, actually. It has a mass of 294.2 gram per mole, and you notice that a larger proportion of the beaker is filled up because each individual unit has 7 oxygen atoms, 2 chromiums, and 2 potassiums. So there are a whole lot of individual atoms in there, and that's why it takes up so much space. and also there's density issues there as well. But the final picture is that for sucrose, C12H22O11, each individual molecule of sucrose, as you can see, has 22 atoms of hydrogen, 11 atoms of oxygen, that's 33 atoms, and throw on top of that 12 more carbons, that's 45 atoms per molecule. That's a whole bunch of atoms in the mole, so it takes up a lot of space. Also, sucrose is not particularly a dense material either, so that's also contributes to the volume. Notice that 1 mole of sucrose would weigh 342.3 grams. That's the sum of the molar mass of its individual parts, as we discussed previously. Let's look at some examples of doing unit conversions, much like you would do in laboratory. If you were asked in a procedure, you were given the number of moles of material needed in a recipe. We don't have mole tweezers. What we do is we go to the scale and we scoop out the equivalent amount of the matter and put it on a scale and weigh out to infer how many moles of the matter we have. So suppose a procedure calls for 3.75 moles of helium, and I go to my periodic table and find helium weighs 4.003 grams per mole. Each Avogadro's number of helium atoms would pile up until it weighed 4.003 grams. So to get 3.75 moles of helium, notice I line the molar mass of helium up as a conversion factor. I want to get rid of the moles and leave my answer in grams. So essentially I'm multiplying by the molar mass in order to cancel the mole units in the molar mass value, and that leaves me in units of grams. So according to the dimensional analysis, it tells me take 3.75 times 4.003 divide by 1, and that would tell me to weigh out 15 grams of helium if I want 3.75 moles. How many grams of sodium sulfate are present in 3.75 moles? Well, again, a procedure calls for that much sodium sulfate to be added. I would first turn to my periodic table, add up 2 sodiums, a sulfur, and 4 oxygens. That would total to 142.05 grams in 1 mole. Again, to get rid of the mole unit in the 3.75 moles I'm beginning with, I'm going to multiply by the molar mass, and I don't really try to memorize that. I just recognize I'm going to cancel the mole units in the conversion, and the only unit left is gram units. So then the numbers tell me to take 3.75 times 142.05 divided by 1. I would need to weigh out 533 grams of the sodium sulfate, in order to get 3.75 moles of it. To do the reverse procedure, which means convert the grams of material into how many moles that are present. Well, if I had to multiply by the molar mass to change moles into grams, I'm certainly going to have to divide by the molar mass to change grams into moles. But really, I would not prefer that you think of it in that fashion. What I would prefer you do is approach the problem as a dimensional analysis problem. The units of the molar mass are conversion factors that can take you from grams to moles or moles to grams, depending on what you want to do. I just have to line the molar mass up in a fashion so that the unit I'm trying to get rid of goes away, so that goes on the bottom, and the unit I'm trying to end up in appears, so it has to be on the top of the conversion factor. So, how many moles of sodium are present if I have 125 grams of sodium? I turn to the periodic table, and it says that each mole of sodium weighs 22.990 gram per mole. So I wish to convert my 125 grams into moles. I take the molar mass lined up so that the gram units cancel, meaning the mass of it goes on the bottom, so naturally the moles of it pop to the top, and I've lined it up so that the G's are gone, algebraically dividing away, and the only unit left is mole. So I will take 125 times 1, divide by 22.990, and I would find, if I weigh out 125 grams of Na, I have weighed out 5.44 moles of Na. If I ask the same question, well, I ask how many moles are present in the same amount, if you like, of calcium phosphate. There's the formula of calcium phosphate. On a slide previously, I found the molar mass of calcium phosphate pentahydrate, but this is just calcium phosphate. If I add up the 3 calciums, 2 phosphoruses, and 8 oxygens for this, I would find it is 310.18 grams in a mole. So if I wish to convert 125 grams of this material into moles, again, I take this molar mass lined up to cancel the mass units of the amount I've weighed out, and that would naturally put the grams part of the grams per mole on the bottom, putting the mole part on the top. G units divide away algebraically. I'm left with only mole units. So once dimensionally everything is lined up correctly, I then know that I can do the operations on the numbers just like I did the operations on the units. So I will take 125 times 1, divide by 310.18, and I would find that 125 grams of calcium phosphate corresponds to 0.403 moles of calcium phosphate, significantly fewer moles than are present in 125 grams of sodium, because there's so many more atoms, meaning so many more electrons, neutrons, and protons in the calcium phosphate than there are in the sodium. Let's look at a couple examples of going between moles and atoms to moles. Let's take the example where we ask, if I have a quarter of a mole of iron, how many atoms of iron do I have? Well, we don't need the molar mass of iron in this case. If it had told me that I had a quarter of a gram of iron, then I would need the molar mass, but here I have a quarter of a mole of iron. So you have to be very careful in reading the problem and understanding which conversion factors to apply. There's no need to apply the molar mass of iron in this case. I already know the number of moles. What I'm asked is how many atoms are in that number of moles. Well, I know in a mole of any type of atom, there are 6.02 times 10 to the 23rd atoms. So if I have a quarter mole of iron, and then I use the Avogadro's number as a conversion factor, the units of it we can think of are moles and atoms. I will line it up so that the mole unit goes away. That means the mole part of the conversion factor goes in the denominator. That naturally puts the atom part of the conversion factor on the top. So now I note that algebraically the mole unit cancels, and I am left in atom units. So then the numbers are lined up appropriately if the units are lined up appropriately. So I'll take 0.25 times 6.02 times 10 to the 23rd, and I'll divide by 1, and that will give me 1.51 times 10 to the 23 atoms of iron are present in a quarter mole of iron. Now, one indication or the ramification of not needing the molar mass of iron here is that it is true that for any material, if you have 1/4 mole of any material, you will have 1.51 times 10 to the 23rd of those things. Meaning, if instead this question had said, how many atoms of copper are present in a quarter mole? How many atoms of zinc are present in a quarter mole? How many atoms of gold are present in a quarter mole of gold? I would do exactly the same procedure and come to the conclusion that there is 1.51 times 10 to the 23rd atoms of zinc, atoms of copper, or atoms of gold present in that quarter mole. It goes even a little further than that. Even if I had molecules present, and I wanted to know how many molecules, say, of carbon dioxide are present in a quarter mole, how many molecules of water are present in a quarter mole, how many molecules of sucrose are present in a quarter mole, I would simply take 0.25 times 6.02 times 10 to the 23rd, and I would find there are 1.51 times 10 to the 23 molecules of water, molecules of sucrose, molecules of carbon monoxide present in a quarter mole of sucrose, water, or carbon monoxide. Now at the bottom of the slide, I look at going through the reverse process. Given that I have 2.2 times 10 to the 20 atoms, how many moles of copper are present in that 2.2 times 10 to the 20 atoms? First of all, I will use the same conversion factor. 1 mole is an Avogadro's number of things. It is 6.02 times 10 to the 23rd things. But this time, since I'm going from atoms to moles, I line that conversion factor up with the atom part of the conversion factor in the denominator, putting the mole part of the conversion factor in the numerator. Notice the atom units cancel. The only unit I'm left with is mole unit. So since dimensionally the units line up properly, I know that correctly I should take 2.2 times 10 to the 20, multiply by 1, and divide by 6.02 times 10 to the 23rd to get an answer of 0.000365 mole of copper present in that many atoms of copper. Okay, now a few things to say regarding this. First, when I am dividing by Avogadro's number, be careful how you enter that into your calculator. Remember, as I talked about way back when we did dimensional analysis, was that when you enter this in, if you type into your calculator 2.2 times 10 to the 20 divided by 6.02 times 10 caret 23, your calculator does not understand what you are doing there unless you group the entire 6.02 times 10 to the 23rd in parentheses. That is the only way to ensure you will be dividing the numbers together. Or, as I talked about with you a long time ago now, you can also use your engineering exponential button, the second EE button. You could type in 2.2 second EE20 slash 6.02 second EE23, and that will give you the answer 0.000365, or it might give you 3.65 EE negative 4. It could give it that depending on how your calculator is set up. Now the next thing I want you to note is that again, in doing this conversion from moles present from the number of atoms present, I did not use the molar mass of copper. This is saying essentially the fact that that number of atoms of copper gives you that given answer of moles, but it wouldn't matter if it was copper atoms. In 2.2 times 10 to the 20 atoms of iron, there is 0.000365 moles. In 2.2 times 10 to the 20 atoms of sodium, there's 0.000365 moles of sodium. Not only is this true for atoms, it's true for molecules as well. If I have 2.2 times 10 to the 20 molecules of ammonia, I would have 2.2 in 2.2 times 10 to the 20 molecules of ammonia, I would have the same number of moles, 0.000365 moles of ammonia, just like I have for these numbers of atoms present. Look at how to find the number of moles of a particular atom in a given molecule. So let's suppose we weigh out 28.5 grams of AlCl3. And the question you are posed is how many moles of Cl are present in this sample? One of the pitfalls I see students doing is going to the table, getting the molar mass of Cl, and then just dividing that into the weight of 28.5 and thinking they have found the moles of Cl. What you have to recognize is that this 28.5 grams reflects not only the weight of a single Cl, it reflects the weight of 3 Cls connected to an Al. So first what you have to do is find the number of moles of AlCl3 from this 28.5 grams of that material. So I can use the 28.5 grams and convert it to moles of the molecule first. So first thing I do is I weigh out find the molar mass of aluminum chloride. I weigh out 3 Cls plus an Al, add that together, it's 133.3 grams per mole for AlCl3. So what I then do is use that conversion factor to change the mass of AlCl3 into moles of AlCl3. So I take my, lining it up, that conversion factor up correctly, put the mass on the bottom, put the moles on the top. I divide by the molar mass, as the dimensional analysis tells me to do. So I take 28.5 times 1, divide by 133.3, and I find out that I had present 0.214 moles of AlCl3. Now that I know this, that's not the end of the question. The question is, how many moles of chlorine do I have? To find the conversion factor between moles of AlCl3 and moles of chlorine, I use the empirical formula. It tells me there are 3 Cls per AlCl3 unit. So this creates a conversion factor of 3 moles Cl per 1 mole AlCl3. If I have 1 molecule of it, there are 3 Cl atoms. If I have 1 mole of AlCl3, there are 3 moles of Cl. So I line that conversion factor up so that the moles of AlCl3 cancel, and I naturally put the moles of Cl on the top. So I will then take 0.214 mole AlCl3 times 3, divide by 1, that will give me 0.641 moles of Cl. Essentially saying, for every 1 mole of AlCl3, there are 3 moles of Cl. So if I have 0.214 mole of AlCl3, I must have 3 times that amount, or 0.641 mole of the Cl present. Actually, this is a problem going in the reverse order. Suppose I know that a sample of calcium nitrate contains 2.15 moles of oxygen. I want to know then how many grams must this sample of calcium nitrate weigh if it contains a total of oxygen of 2.15 moles. So let me talk about the strategy first. I know how many moles of an atom of the molecule I have present. I can use the moles of a particular atom in the molecule to find the moles of the molecule. Once I find the moles of the molecule, I can then find the grams of the molecule using the molar mass of the molecule. So I need to know the molar mass of calcium nitrate, and of course is 164.1 gram per mole. Maybe not of course, but if you add up 1 calcium, 2 nitrogens, 6 oxygens, that's what you should find. Then the first thing I'm going to do is take the number of moles of O present and convert it to how many moles of calcium nitrate must be present to have that number moles. If I look at the empirical formula of calcium nitrate, I see there are 6 moles of oxygen per mole of calcium nitrate. I use that as a conversion factor. I want to change, I use the 1:6 ratio by getting rid of the moles of O and converting them to moles of calcium nitrate. So I will divide by the moles of O in 1 mole of calcium nitrate. So I take my 2.15 mole of O and take that times 1 and divide by 6. That tells me in that number of moles of oxygen, it must be present only if I have 0.358 moles of calcium nitrate. Notice if I multiplied 0.358 by 6, I would get 2.15 moles, which would be the total of 6 times as many moles of calcium nitrate. So once I have my moles of calcium nitrate, I line the conversion factor of the molar mass up so that I cancel moles in my moles of calcium nitrate, meaning I multiply by the molar mass. That says take 0.358 times 164.1, divide by 1, and I find 58.8 grams of calcium nitrate. All right, I turned off my phone, sorry about that. Where I have when I'm done, I get 2.02 grams of phosphorus. Second, I wish to know how many atoms. So let's look at our bottom conversion factor. Now, how many grams of calcium are present from moles that I have an 8.2 and I didn't need the molar mass. 10 to the 21. When I'm going from grams to atoms, sample the molar mass of the material. Now I'm going to need two conversion factors to do this different as well. Materials. I'm going to need Avogadro's number of atoms of them in 1.03 grams. So if I have 1.03 grams of and I'm also now 3 grams. Since I'm working with calcium instead of phosphorus, grams of boron. Each of them would have calcium, which I find from the periodic table because 40.08 of them gram individual atoms weighs. So I begin with my 8.2. So in order to 21 atoms, 1.03 grams in my first phosphorus aligned to how many atoms are present. Atoms. I'm going to need change to moles. Conversion fact. So I use my first is the molar mass of phosphorus lined up so that I get Avogadro's number itself is on the bottom 30.9 attached to the atom unit per mole. The second is Avogadro's number. That ratio says that 1 mole of anything there, I would have the number 6.02 moles 10 to 23rd of those calcium that are in my 8.2. So the first thing I can do with my atom sample mass, but what I do after that then is I convert divide by the molar mass, multiplying by the molar mass, eliminate the grams, and convert my answer into moles. Now again, why did I choose phosphorus? Why didn't I divide then by I can multiply because I wish to eliminate the mole unit. The reason I choose the molar mass has to be lined up. Avogadro's number of the molar is that I am eliminating the mole unit. That means naturally the grams of the molar mass in atoms. So notice again, before I put the numbers together, let's note multiplications and divisions. Atom units that I do towards the middle of the slide. This is purely dimensional analysis. Only the gram unit beginning with units of grams. When they're lined up like this, the first conversion factor, like I eliminate from the gram unit of atoms and change me to moles. What it tells me to do. If I stop there, I will get my answer in 1 times 1. Then I apply the second 40. Divide by 6. Change atoms times 10 to the 23rd. Atoms or vice versa. Divide by 1. The end of the first conversion puts me in an answer of moles. 23 atoms. So I line calcium conversion is 0.548 grams. With its mole component on the bottom and its atom. One more time, I will point out to you that you must be very careful when you're dividing by units are gone. You have to mole units are gone. The entirety of that number unit which remains is atoms of P. You have to use your engineering which is what I'm trying to get. And you could type 6.02. Dimensionally speaking, E23. The units that will divide by that number tells me correctly. If I'm doing the recipe of combining the conversion factor correctly them in your to get to the answer. There's no formula. There's no true memorizing a formula of how to do this. You have to solely logic your way through it and line up the conversion factors correctly. So once I can assure that the conversion factors are lined up correctly, the numbers tell me that go along with those conversion factors to take 1.03 times 1, divide by 6. I'm sorry, I got my phone ringing here. In this example, from the mass of a sample of ammonia, I am asked to determine how many atoms of H must be present. This will actually require the use of 3 conversion factors. Again, I could string them all in a straight line to get the correct answer, or I can do it stepwise. And on this particular slide, I do this problem in 3 individual steps. I am starting with 20 grams of ammonia. What I can do with the 20 grams of ammonia is first, I want to get to atoms of H, but I don't simply first find there's 3 moles of H per, and use that as a conversion factor. I need to find from the 20 grams of material, not the moles of H directly, it will tell me directly the moles of ammonia. So I find the molar mass of ammonia, and that turns out to be 17.03 grams. Then I divide the mass of the entire sample by the molar mass of ammonia to find the moles of ammonia. So the first conversion you see is I'm eliminating grams, changing into moles of ammonia. And I find 20 grams of this sample is 1.17 moles of ammonia. Now that I know the moles of ammonia, I can use the empirical formula of NH3 to change moles of ammonia into moles of H. There are 3 moles of H per mole of ammonia. I use that as a conversion factor, lined up to eliminate the ammonia and end me up in moles of H. So I take my 1.17 moles of ammonia, lined up with a 3-to-1 ratio of H to NH3, eliminate the NH3, and in 1.17 moles of ammonia, there are 3.52 moles of hydrogen. Now that I know the moles of hydrogen, I can convert those into atoms of hydrogen by multiplying by Avogadro's number. How did I know to multiply by Avogadro's number? I'm trying to eliminate the mole of H unit and end up an atom of H unit, so Avogadro's number is lined up accordingly. So the moles are now gone, I end up in atoms, and I find 2.12 times 10 to the 24 atoms of H. Again, this could all be done in one individual step, where you line all 3 conversion factors up at once, or it can be done individually as I show on this slide. Look at the example of converting the grams of a particular material that I have present to how many electrons that mass of material contains. So I happen to begin with 21.6 grams of potassium. I know the following things are going to be needed to be done. To find the number of electrons present, I'm going to need to know how many electrons are on each potassium atom. So I can find that out from the periodic table based on a neutral potassium atom having the same number of electrons as the atomic number of that atom, because that atomic number tells me the number of protons. So I find there are 19 electrons of potassium per atom. But in order to get to each atom of potassium, I need to use Avogadro's number to convert from the number of moles of atoms to the individual number of atoms. But to get to the number of moles of potassium, I have to convert the mass of potassium into the number of moles. So this process of going from electrons, from the mass of a sample of an atom, a particular atom, into the number of electrons that are present in that sample, I need 3 different conversion factors, as you see here. The molar mass of potassium, Avogadro's number, and the number of electrons per atom of K. Now, in this particular instance, unlike what I did on the previous slide, I'm going to line them up in one fell swoop and calculate the answer all at once. I begin with my 21.6 grams of potassium. I eliminate the grams of potassium by taking the molar mass. Essentially, I'm dividing by the molar mass, lining up the grams on the bottom, moles on the top. If I stop there, my answer would be in moles of potassium. I apply the second conversion factor to take my moles of potassium into atoms of potassium. That is done by multiplying by Avogadro's number. The reason I know to multiply by Avogadro's number is I'm trying to eliminate the moles. So the mole part of that conversion factor goes on the bottom. That naturally puts the number of atoms in that mole on the top. If I stop there, my answer would be in atoms of potassium, but I wish to find the electrons in those atoms, so I turn to the periodic table. Since potassium is atomic number 19, a neutral potassium atom has 19 electrons. 19 electrons per atom constitute a conversion factor, which I line up with the atoms on the bottom, the electrons on the top. So notice before we do the numbers, the gram units are gone, the mole units are gone, the atom units are gone. The answer comes out in electrons. So if the units line up correctly, so do the numbers. So I will take 21.6 times 1 times 6.02 times 10 to the 23rd times 19 and divide that all by 39.098. And that tells me there are 6.32 times 10 to the 24th electrons in my 21.6 gram sample of potassium. Let's look at the approach to essentially doing the same problem of the previous slide, but now doing it in reverse. This time you are given a certain number of electrons, 1.58 times 10 to the 19 electrons, and you are asked to find how many grams a sample of those electrons that are in a tin plus 2 cation must weigh. Well, first of all, what you're going to need again are 3 conversion factors to pull this off. You are going to need to know how many electrons are present in a tin plus 2 cation. Now remember what we spoke about in our previous unit is that a cation is formed not by adding protons to the nucleus. A cation is formed by removing electrons from an atom. So from the periodic table, a neutral tin has 50 electrons. So a tin plus 2 cation must have 48 electrons. So I can use this to convert my number of electrons into the atoms of tin plus 2. Then in order to get to the grams of tin plus 2, I must first take my atoms of tin plus 2 into moles of tin plus 2. I do that by employing Avogadro's number. And once I get into moles of tin plus 2, I can convert that into grams of tin plus 2 by using the molar mass. Here I'm using the molar mass of tin of 118.7 gram per mole. Well, the first thing you might recognize is that that is not the molar mass of tin plus 2, that's the molar mass of tin. And we're missing quite a large number of electrons when we determine that mass. Well, what I would point out to you is that the mass of an individual electron is so light, as a matter of fact, it's about 1,800 times lighter than the other nucleons, the neutron or the proton, that even leaving out that huge number of electrons from the sample, it will only change the significance of this tin molar mass into the fourth digit. So I don't feel slighted by using the molar mass of tin, even though I'm removing this, I've removed a huge number of electrons from the sample because each atom is down 2 electrons in the sample. Okay, so I have 3 conversion factors that I need to apply, and what I do below is line them up all in one complete continuous approach. I begin with my 1.58 times 10 to the 19 electrons. I use the electron conversion factor by putting that in the denominator, and then I use my Avogadro's number again by putting it in the denominator, and I put the molar mass of the compound in the numerator. Now you might say, well, how did you come to the conclusion to do that? Did I use a formula to decide how to do this? Again, I will remind you, this is strictly done via dimensional analysis, looking at the units, lining up the units correctly, and making sure I get from my start point to my end point dimensionally before I combine the numbers. The first conversion factor eliminates electrons and would change the answer into atoms. The middle conversion factor eliminates atoms and would change me into moles. The third conversion factor eliminates moles and gets my answer into grams, which is what I was asked to calculate. The only unit remaining is grams, so all conversion factors must be lined up correctly because the dimensions of the problem tell me they are. So therefore, the numbers are lined up correctly. I need to take 1.5 times 10 to the plus 19 times 1 times 1 times 118.7. Then I'll divide by 48, divide by Avogadro's number, and divide by 1. And this will tell me that I will get 0.0000649 grams of sample, or 6.49 times 10 to the minus 5 grams of the sample of tin plus 2. One more time, I will remind that when you're dividing by Avogadro's number there, you should either use parentheses around that number when you hit slash in your calculator, or you should use the engineering exponential key in order that you put the number in there correctly and you're not eliminating or multiplying by 10 to the 23 instead of, as you're supposed to be doing here, dividing by it.